Here is a teardown of a rotary compressor. This is the stator and suction port. The single-vane spring load chamber contains a piece of aluminum pipe so it can be identified. With the bolts and top plate removed, here is the discharge reed valve. Removal of this component reveals the sliding vane, rotor and eccentric on which it rotates. Here is the suction port again. Through here, the spring load for the sliding vane is situated. This is the discharge port through which high-pressure refrigerant is ejected. The aforementioned reed valve, a check valve, is situated on top to prevent backflow. Here, I am putting back the rotor onto the eccentric. And, last but not least, in goes the sliding vane. As the rotor moves, it creates a void where refrigerant is pulled through the suction port. This void progressively increases along the rotor's revolution within the chamber. The sliding vane separates high and low pressure regions, maintaining its seal with the stiff progressive spring load keeping it against the rotor's outer circumference. Oil that flows through the refrigerant loop not only lubricates moving parts, but it also assists in forming a seal between the rotor and internal walls, as well as a seal between the vane and outer circumference of the rotor. As the rotor revolves, the chamber volume begins to increase. This progressive increase in volume creates a decrease in pressure for intake of refrigerant through the suction port. As the rotor revolves, eventually it reaches a point where the chamber is at maximum volume. Progressive rotational movements result in the rotor moving past the sliding vane, sealing off the volumetric mass and commencement of its compression for ejection through the discharge port and reed valve. The cycle repeats itself. Generation of low pressure via progressive increase of volume commences on the next side of the separating vane, creating suction for refrigerant intake. Let's take a concluding look at the operations.